can reach about 40%. So the problem of inversion is incorrect, which leads to the need to apply regularization. In this case, reflection coefficient traces with the smallest number of non-zero components are preferred. Thus, an objective functional appears consisting of the norm of the residual of the synthetic and the observed seismic traces, as well as two stabilizers that impose a penalty on the total variation of the solution. To take into account the migration velocity model in the solution, one more stabilizer was added to the objective functional. This one. And since the inversion is formulated within the framework of one-dimensional model, it's important to keep in mind the spatial connectivity of the model to ensure the smooth change in reservoir properties within the layers of the model. Another stabilizer was introduced that relates the solution for the considered path to the solution for the adjacent path from the point of view of low contrast approximation. So thus the objective functional of the inversion of the total variation with restriction has the following form. And to minimize the functional, the iteratively reweighted least squares method is applied. So after we created the 1D seismic inversion, we applied this inversion to the synthetic data for the 6B model got by one-dimensional and two-dimensional convolutional modeling. As shown above, they slightly differ from each other at the interfaces, but has significant difference in the area where the scattering diffracting objects are located. The same effects appear when we compare inversion result. And for a more detailed comparison, we calculate the error of the inversion results relatively to the acoustic true impedance model, and 1D inversion of YD modeling data provides the inversion result with the minor error. We get such result because 1D inversion and 1D modeling are inverse operations with respect to each other. However, the result of seismic data processing in a 2D media correspond to 2D convolutional modeling. So it is necessary to track the corresponding errors which arise during 2D seismic data processing. And one can see that the inversion of 2D modeling data provides error about 3–8% in the most of the media, and the error can reach 60% like this. And here, in the areas with scattering objects generates significant errors. This means that 1D seismic inversion must not be applied for reconstructing of scattering objects, particularly for fracture model reconstruction. Therefore, based on the described above results, we suggest investigating the inversion that uses the 2D convolutional model. And from practical data sets, we know that fractures provide localized heterogeneities of the elastic properties. Therefore, the fractures on the seismic model scale can be considered as scatterers diffractors that are scattered in diffractive part of the model. And this part of the model is the reconstruction goal. On the other hand, we have the result of the seismic data processing, which is the depth seismic image. And as we said above, this image in the 2D case satisfies convolution model. Therefore, we create a rather big number of different 2D localized fracture models, then put this fracture model inside reflector model, and finally provide the corresponding seismic image. We provide models and images easily using rather small computational resources and minimum a priori information about fractures. Thus, we construct training data set for the machine learning algorithm. And we interpret the fracture reconstruction problem in terms of machine learning as a semantic segmentation. It means that to classify each pixel to belong to a background is a 0, and to fracture to 1. We use the unit neural network architecture to solve the problem and modify the architecture to work with 2000 by 400 input-output size. Also, we defined two variants of loss functions. First is dice loss, and the second is the equal combination of dice loss, binary cross entropy, and mean squared error loss, which averages on all pixels of the image. And to test the technology, a two-dimensional seismological model is created based on a prototype section of one of the East Siberian fields. Small-scale heterogeneities, these ones, typical for this field, are included in the model. These are fractures located in the upper part of the riphane carbonate complex. We can create a variety of different fracture models with the information from the well data. In this particular case, we construct 1,000 models. For all of them, we construct corresponding full models, including reflective part of the model. That is the same for all 1,000 fracture models. And finally, we provide 2D convolution modeling in order to get the ideal image. So then we come to the experiments, and in the first experiments from the data set, we use 800 realizations for training and 200 realizations for testing. Neural network training parameters are the following. So learning rate is 0.1, batch size is 1, maximum number of epochs is 60, and we carry out validation on test dataset at the end of training after the 60 epochs. And in this case, we use dice loss functional only. After we finish the training, we apply the trained neural network to the images that were used in the training dataset first. One of the images and the corresponding recovered model results are presented on the top of the slide. Recovered fracture.
You have 2 minutes.
Okay, I'm almost done. Recovered fractures location have red color. The true fractures location have blue color. There is rather good correspondence between the biggest true fractures location and the recovered ones. Dice metric in this case is rather high, and it equals to 23.2%. And then we apply the trained neural network to the images from the testing dataset. The total error in the training was 0.75, and on the test 0.753. One of the images and the corresponding recovered model results you can see on the bottom of the slide. There is also good correspondence between the biggest true fracture location and the recovered ones, and dust metric in this case is rather high, and it equals 25.5%. So in the next experiments, almost was the same. The main difference was that we use now combination as a functional. We use combination of dice loss, binary cross entropy, and mean square error loss, and the result in this case becomes a bit better. So dice metric in this case is rather high, and for testing data set, for training data set, it equals 37%, and for testing data set, it equals to 28.8%. So, and finally, I come to the conclusions. Briefly, so numerical, we provide numerical study and show that 1D convolutional modeling and 1D inversion cannot be applied for the recovery of the fracture model. It cannot be applied for fracture model reconstruction, and we provide methodology based on machine learning and 2D convolution model, and we show that on 2D models, on realistic synthetic data, realistic synthetic model from Eastern Siberia, that the results show appropriate reconstruction of the fracture model, and this result look promising for the generalization of the approach to 3D real physical models. And finally, I have to acknowledge the RSF. It was the work was supported by RSF grant, and thank you for your attention, and I will try to answer your question. Hello? Do you hear me?
Yes, we can hear you.
Okay, thank you very much. We just gave you some claps, but the mic was off. Sorry about that. And we can take some questions from the local participants. You have to come here, and or for the remote participants. So we will have a first question here. Just a second. Can you please introduce yourself and just go ahead?
Yeah. Thank you for your talk. It was great presentation. I have a quick question. When you add additional convoluted data to your model, do you think you might have certain kind of biasness on detecting of the fractures? The second question is how you choose your training and testing data sets. Is it kind of some way of the random selection, or is it kind of the specific location that you don't know and you have a data where you know the fractures? That's the way of your selections. So that's my second question.
Okay, so let me try to answer your question. So
that's correct. You mentioned here 2D convolution is creating for training data sets. So the question is it kind of sort of biasness?
So I'm not sure I understand your first question because so 1D convolution this is 1D model, and because this kind of models is really 2D, and we have in this case 2D effects, and 1D modeling, it doesn't describe it, and the 1D inversion also cannot take into account. That is why we come to 2D convolution model.
My point was 2D was generated by you, so that's kind of synthetic. Okay.
Here because this is synthetic example.
Okay. Yeah.
So in this case, because our true model that we have, we also use the 2D convolution model. In this case, so we are within the same modeling, I would say. So to come to the real data, it's another step, and we have to be, I would say, more accurate. We have to be sure that our 2D modeling gives appropriate results. So I think so. But because formulation of when we construct seismic image, and we've got the formulation that this is 2D convolution is really corresponds to the our migration operator. So we think that it should work also on real data. And now we now working on real data, and we see that that some promising result we can get here. And maybe let me come to the second question, because why we think this can be applied. So we don't try to find the fracture model, whole fracture model. We use a priori information, and as you ask, we know where fractures are located. So as you see here on this example, we know that this is Riphean carbonate complex, and we know where is it located. And the background model, we know background model also from the data processing, seismic data processing. And the goal here is to understand, to describe as good as possible the fractures, their size, their locations, and this is information that we have on seismic image, and we're trying to extract this information from seismic image. So locally, so we solve the problem locally.
Yeah, that's good. Thank you. So it was randomly selected, right? Training.
Yeah. So we know from the well data, we know what kind of fractures we have. So we know what kind of properties inside fractures. So and we try to detect the geometries of the fractures to not fractures itself, but the objects that on seismic data fractures are presented.
Okay, Maxim, thank you.
Thank you very much. Okay, Maxim, thank you again.
Okay, thank you.
Okay, you can stop sharing your presentation. And I'd like to call again now Dmitry Nekrudov. Dmitry, can you hear me?
Yes, I'm here.
Okay. Can you please share a screen?
Yes. Как тут у меня вот? It will take some time. Видно-то меня? Не видно? Что сделать, чтобы...
Yeah, that's only mic. Okay, mine is off.
Sorry. Sure. Do you see my screen?
Dmitry, I can see you screen. Can you put that in full screen mode?
Yes.
It's very small here.
Is it okay?
No, it's the same size.
Yeah, I think you shared the wrong screen.
Yeah. There's a setting on your side.
Sorry, but my screen is full. I don't know what.
Yeah. Just choose the right window when you share using Jitsi.
Yeah,
You can choose your window.
just sharing the windows instead of the other. So
Yes.
Dimitri, make sure you're sharing the full screen mode because it's only the window at the bottom that we're seeing.
Okay. Stop sharing.
Okay, getting better. Now the video's off.
Full entire screen. Share.
That's okay.
Oh. So I can start.
You know, it's not showing. It's just a blank screen now.
I'm seeing his presentation.
Do you
here.
see my screen?
Yeah, I can see your screen. Yeah, in full screen.
Refresh.
Там нормально?
I'm sorry.
Excuse me, do you see my screen?
I can see your screen here.
Okay, Dimitri, you can see it. So your presentation is going to be fat rays in three-dimensional media to approximate a broadband signal operation. We can see the screen, we can hear you, you're good to go. You have 50 minutes, thank you.
Okay, many technical applications require calculating travel time and travel path between known locations of source and receiver. In seismic exploration, such a problem, known as ray tracing, plays a significant role. Data processing techniques, seismic data processing techniques such as depth migration or seismic tomography should be computationally efficient. It means that ray tracing subroutines, which are part of any seismic data processing packages, must be effective. Ray-based methods are usually are usually used high-frequency approximation of seismic signal propagation. Classical array method doesn't take into account the effects caused by the fact that spectra of real seismic signals are band-limited. High-frequency approximation often leads to the non-physical behavior of rays and corresponding travel times. Here is a very quite simple example of non-physical behavior of standard high-frequency, so-called, I call it high-frequency rays in complex medium. Here we can see salt bodies, salt intrusion. It's a well-known 6B velocity model. As one can see, ray distribution are very irregular and looks ugly. The limited spectrum signals propagate within some volume surrounding the ray. It is so-called Fresnel volume. Dominant frequency of the signal determines the width of this volume. A number of methods are developed to go beyond the standard rate method based on high-frequency approximation. The main idea behind these approaches is to consider the impact of the Fresnel zone on travel times and ray paths. The principal disadvantages of all proposed approaches is the complexity of calculation. It is especially important in three-dimensional case. The most common limitation is complexity. So, the original approach for approximation the propagation of broadband seismic signal in complex environment was proposed in this paper. Lomax paper, French seismologist. This method was called as the wavelength smoothing techniques. The key point there is that velocity used for ray tracing is determined by smoothing actual velocity along the normal to the ray at the current point. At the current point on the ray, and smoothing is performed over some aperture which is proportional to the wavelength. Here we propose quite simple and robust algorithm to construct frequency-dependent rays in complex 3D medium. We call it FAT rays. I will explain below why we call it in this manner. This method consists of two main ingredients. First is the wavelength smoothing proposed in Lomax paper. These techniques allow us to calculate locally smoothed velocity in the vicinity of the ray. And the second concept is the local control point movements, which is used to determine the ray propagation vector at the next point of the ray. As an input of the procedure, we defined some auxiliary parameter nu measured in hertz. We called it frequency of the ray. This parameter determines sensitivity of the ray to velocity variations. So, as an input of the procedure, we need to define two takeoff angles, azimuth and dip. Let the point xp is a current point on the ray. We will call it a central point. At this point, a unit tangent vector s is defined, which define a ray propagation direction at the current point. To move along the ray, they need to define new position on the ray and new ray propagation vector. So the first problem is how to define new position on the ray. We construct a plane passes through the point xp. This plane is orthogonal to the normal vector, to the ray direction vector s. In this plane, we cut a rectangular area. The size of the rectangle of this patch is a function of local wavelength in the central point. Local velocity values is defined on the regular grid on the point of points in this patch. Here I mark it as blue stars. Smooth velocity at the central point is calculated using this very simple formula. This is just simple weighting. Weights as a dating function, we choose 2D Gaussian function. Here we have distance between central points and points in the patch, and into a couple of parameters, wavelength in the central point and some auxiliary parameter alpha, which allow us to modify the shape of the smoothing function. In this slide, I present 2D Gaussian function used for velocity smoothing along the front for different parameter of alpha. Then parameter alpha is small, the smoothing function becomes narrower. It concentrates near the central point. Then increasing parameter alpha, the Gaussian smoothing is reduced to simple averaging in rectangular area. Sorry. So now we are ready to define new position on the array. So we have calculated smoothed velocity. Here we have direction of the movement, and we have direction in the central point. So during the time interval dt, the central point moves along the vector s to the new position. It gives us new position on the array. Now we need to determine new ray propagation direction vector s new in this point. To do it, we introduce a concept of so-called control points. We consider a circle lying in the same plane orthogonal to the current position direction vector s here. Radius of the circle is also a function of the local wavelength. We choose a number of points lying on the circle with constant angular increments. We call these points as a control points. So in each control points we calculate corresponding smoothed velocity using the same plane as for central points. So now each control point is attributed with independent and different smoothed velocity value. So and now for the same time interval dt, each control point will travel different distances along direction s. So each point comes to its independent position. Here we can see new position of control points in 3D space. I would like to emphasize that now new position of the control points are not in the same plane, maybe not in the same plane. So we need to define numerically a plane which is closest to all these control points, new control points, in the least square sense. Thus we need to solve classical three-dimensional linear regression problem. So we can find such a plane. We can define normal vector to the plane, and we will call it as a new ray propagation direction. So and finally we attribute this. We attach this vector to the central point position. There is a step-by-step movement along array. Here I would like to note that fat ray tracing is performed in a certain volume of the medium. That's why we call this ray as fat ray. Simultaneous movement of all control points determines the next orientation of the front. So now I would like to describe simple numerical experiment. In seismic exploration application, one of the most challenging situations for the ray method occur then the salt intrusions are presented in the model. Because salt bodies, salt intrusion might have a very complex shape. Seismic wave velocity in salt is much higher than in sedimentary rocks surrounding an intrusion. Usually it is very problematic to construct reliable rays passing through the salt bodies and to calculate corresponding travel times. below we show that race can resolve these issues. This slide presents a well-known 3D ECG salt velocity model with a salt body of complex shape. Salt body is shown in red. Top of the model is a water layer. Seismic wave velocity in salt is 4,500 meter per second. Meanwhile, in surrounding area, it doesn't exceed 3,000 meter per second. So we want to calculate the corresponding race. We would like to calculate race and first arrival travel times in each point on the regular velocity grid. It is so-called travel time tables. For standard retracing, we use the code taken from well-known Madagascar freeware package. Fat race are calculating using our code. So next slide is, in this slide, I show 3D view of 15 race calculated for a fixed azimuth angle. Azimuth angle is equal to 0 here, and uniform deep angle increments. One can immediately note that standard and fat race are substantially different. Behavior of fat race looks much more regular. I will prove it below. And note that race behavior are substantially three-dimensional. Rays go far beyond the plane where the source is located. So here is the main picture, main figure of presentation. Is comparison of travel times. To calculate travel time tables in the whole model, we must shoot the rays quite densely with small deep and azimuth angle increments. Here we used a bunch of 500 by 500 rays in azimuth and deep direction. In this slide, I show travel time tables for each method. Standard, as one can see, standard rays produce holes in the travel times. So there are areas where the rays do not arrive at all due to complexity of the model and limitation of the ray method itself. In these areas, travel times are equal to 0. Blue area. It is obvious contradiction with the real physical process of real wave propagation. Right figure shows the fat rays travel times. Fat rays pass through the salt bodies and produce quite regular distributed travel times. The residual between the fat rays travel times and exact first arrival travel times provided by finite difference method or scalar wave equation do not exceed 6 milliseconds, which can be considered quite satisfactory. And the last example is acoustic wave field simulation in the frequency domain.
You have 3 minutes.
Okay. Here we compare results provided by ray method and exact solution of Helmholtz equation. Here I skip this thing. There is smooth velocity model which we use for this experiment. Here is a comparison of acoustic wave fields in frequency domain for frequency 5 Hz. We can see good agreement between them. And here is my conclusion. Fat rays allow simple and efficient approximation of the broadband signal propagation. Comparative analysis of fat and standard rays in complex environment was performed for travel times and wave field simulation. The results show the prospect of using 3D fat rays in seismic exploration programs. Here is my acknowledgement. The reported study was funded by RFBR grant, project number. That is all. Thank you.
Okay, thank you very much. We can take questions from the local presenters or remote one.
Yes, I'll try to answer.
Okay, I have a question for you. It's not exactly my field, but I can appreciate more or less what you're trying to do. Can you go back to slide number 11, please? So I was good until this point, and you say that the velocity is different from each of the control points.
Yes, because
right?
usually, sorry.
each of the control points may have a different velocity to
Yes,
calculate.
of course.
How do you get the velocity?
There are two possibilities. First possibility is to use smooth velocity model, smooth velocity, which is calculated in the same manner as for central point. Again, we locate, for example, consider this point. Again, we can we can construct a plane. We can collect, rectangular area in this point with the center in this point. We can collect velocity values from the patch and use this formula for smoothing.
Okay.
Each point has its own smooth velocity. It is first possibility. Second possibility is just to use original initial velocities, but they will be different because our models are three-dimensional.
Okay. On the next slide, you showed that you do a flattening. You do a regression to make them on the same plane, on a new plane.
Yes.
But all of them are going to be on a new plane. You're not going to get any outliers.
No, generally they are not. They will not be in the same plane. So which is why we need to approximate their position by using linear regression.
Okay, I see. Thank you very much. Do we have further questions? So we don't have further questions, Dimitri. I thank you again for your presentation.
Thank you.
And I'd like to call the next presentation on this session. That's visualization analysis and collaborative discussion of civil weather events. From Diego is going to present us. Diego, thank you very much. You have around 15 minutes for the presentation, and I'm just going to shake my hands if you pass the time. Okay. Go ahead. Thank you very much.
Can you hear me? Hello? Rafael, can you hear me?
Okay.
Can you hear me clearly?
I can hear you.
Okay.
And I can see your slides. So you're good to go.
Okay, thank you. Hello, everyone. My name is Diego Dias. I'm professor at Federal University of São João del Rei in Brazil. And I'm one of the authors of this paper, and I'm going to present here for you. This paper was conducted in partnership with some Brazilian institutions. You have here two federal universities, UFSJ, where I'm a professor, and Unifesp. You have two universities in São Paulo State, Unesp and Unoeste, and CIMEPAR, a meteorological institution of Paraná. The World Meteorological Organization provides many guidelines and information systems that provide early warning into severe weather conditions, like weather events such as tornadoes, wind, rain, temperature inversions, and lightning. And those bring several consequences to the city population, either on economic or health aspects. The primary purpose of such guidelines is to help the construction of tools and rules for preparing the National Weather Service worldwide to deal with severe weather events. And that is the case of storms followed by floods, especially in urban areas that cause a lot of mortality due to drowning, landslides, and buildings collapses. Severe weather is either becoming more frequent or reported more often. Thus, it's necessary to have appropriate computational tools to help specialists visualize and analyze such events to prevent death and loss of property. Computational tools are necessary to define research for prevention and the anticipation of weather events, minimizing damage caused by severe events. Although technological advances have made it possible to tackle complex problems in diverse areas, such as those related to weather, it's still a challenging task to design and develop systems to assist in visualization analysis and collaborative discussions of severe weather events. In this paper, we present a web toolset for the visualization, collaborative understanding, and analysis of severe weather events. So you have here the visualization events composed on maps tool called VMaps, that is also known as viewing events on maps, which provides a user-friendly environment that allows users to interact with weather data and analyze severe weather information. And this tool set also includes the collaborative system for meteorological data analysis tool, also known as Cometa, that allows collaborative analysis and discussion between remote users in a synchronous way where everyone interacts in real time, or in a synchronous way where the interaction can be distributed over time. And we also conduct some usability tests where we applied to develop tools through an evaluation guide by 5 experts. We found some related works which we were conducting our research, and we found some results concerned to data analysis, mitigation of natural hazards, all sorts of extreme weather events. And these studies describe the intrinsic characteristics of the associated weather phenomena concerning the evidence of natural disasters. We investigate studies that bring alternatives or innovative ways of using technology for weather data analysis or the prediction of severe weather events. We found some technology described in such studies include all types of sensors such as radars, satellites, and meteorological stations, lighting sensors, numerical weather prediction model data. We found some studies regarding to the highlights the meteorological conditions and how it affect the aircraft, for example, weather data visualization system capable of performing pre-process, transformation, and rendering, visualization approach to analyze three-dimensional atmospheric front structures, 3D environments to visualize the cyclonic storm Chapala. That's the example. Chapala was the second most robust tropical cyclone on record in the Arabian Sea. And we also found some studies that applied virtual reality to visualize an interaction in weather-related content. But all these works has a common gap in the reviewed, that is the lack of collaboration between remote users. And the value of collaborative analysis of severe weather events proposed here lies in the exchange of information to improve the understanding of underlying features in the multi-source data. And the research is focused on building a collaborative solution to be used in practice. Here we have the VMAP architecture. We have 4 models. The visualization model is the first one, which provides 2 types of interaction, global and specific. The global ones refers to manipulating the angles of the map, facilitate visualization of the terrestrial globe and in its objects. Specific interaction occurs when the user hovers over the particular map area, and users can visualize and analyze the data using maps enriched with multimedia elements, such as glyph icons, text, images, videos, and so on. The users can view and analyze data using 2D maps and using also combining with 3D representations. The second model is called engine model, which consists of algorithms used to manipulate the data. So here we have mapping of multimedia elements that are superimposed on the environment. We have data mining that allows users to manipulate the database by applying some filters such as level of rain accumulation, humidity, lighting. You have the database model used to store the severe event data from different sources, and the web technologies used to implement all the backend solution. We use HTML5 and JavaScript, as they can use to develop complex and very nice web applications compatible with all major browsers, even non-mobile device. VMaps, we can use some of the most important maps provider with VMaps. I can mention you Microsoft Bing, Google Maps, and OpenStreet Community. And usually these maps also offer API that is a set of functions, classes, methods, and can be used without a lot of deep understanding about the details of the implementation. And use the APIs in real time, we can have the satellite images and their coordinates, computational methods for requesting data. For example, we can have a latitude, longitude of given place, and different types of satellite images, among others. Here we have the hierarchical navigation in 2D maps. We used a solution based on quad trees and it allows the user to select pieces of data, like subsets, according to a specific interest. So this feature was implemented using Celsius.js framework, and the implementation of hierarchical navigation with maps was based on the camera distance concept of the globe. So the smaller the distance, the greater the level of detail. And when there is an inclination of the camera on the map, different tiles levels are presented to the user. The slope is user interactivity function with the map, allowing the user to view the glyphs and depth, facilitate the analysis process. Here we have an example, the operation of the maps. You can demonstrate here some real data of lightning flashes on January 1st, 2014. A mesoscale convective system quickly developed over south of Brazil, being associated with a cold front active in the region. And this weather system propagated from Paraguay to the Brazilian East Coast in Santa Catarina in about 2 hours. And it brought many severe weather activities, including strong thunderstorms and lightning, like depicted in figure 1 here with the red dot. The civil defense authorities had to warn the population about floods and landslides in 13 cities in the eastern portion of Santa Catarina, as reported by local newspapers. In the map's graphical user interface, the user can view the globe using different maps, as I mentioned you, and icons are available to allow search by address or specific patterns. It's also possible to return to the starting point of the visualization, change the map image provider or the visualization parameters like weather, events, electrical stars, and data ranges for viewing the events, and view the map's quad 3D visions as well as information. In this figure, you can see the data related to meteorological events captured by automatic ground weather stations in Brazil, the southern part. And by clicking on weather station, that is represented by the small antenna, users are presented with a window, the left side here, showing data captured by the station, such as wind direction, atmospheric pressure, rainfall accumulation, air humidity, and so on. And we have the option box, the right screen here, the right layer. The user can select the details in which they are interested. We also create a different systemic action to increase the user attention based on 3D interactive maps. And we intended to facilitate interaction between the views of details and context, seeking to decrease the cognitive load and increase the rate of capture of information. To achieve this goal, we create an interactive three-dimensional just pose context environment to present the relationship between various data related to meteorological events. So we use the information regarding latitude, longitude, and others to capture all the events from the stations. And the information can help create three-dimensional representations that can support and analyze the complex sets of information for quick, accurate, and safe decision-making. Here we organize the 3D representations in a tree structure, following the quad tree groupings, as I said, where the leaf nodes have no other subdivisions. So this form of organization allows different depth levels and contents, so that the lower the depth level, the more detailed the region observed will be. And it's worth noting that the representations show the viewer's direction and angles connected by lines that visually link each secondary representation to its source, creating a easier hierarchical structure. Here I have some link. I cannot show you now the video because it's a little bit long, but you can take a look later and see the experiment we conducted. And about the usability test, according to Nielsen, the best results from usability tests comes from the small test with no more than 5 users. So Nielsen proposed some heuristics, and some of them had to be adapted to our research. We had a group of 5 experts that are specialists in visualization and analysis of severe weather events performing the following steps in the usability test. The first one, they are accommodating the computer laboratory. The second, the experts fill out a pre-test questionnaire which aimed to identify their profile, age, sex, education, technology, literacy. And third one, the maps was explained by an instructor for 30 minutes. The fourth, each expert had 13 minutes to use VMAPs, and since the experts fill out the usability questionnaire, each one had 15 minutes to complete the questionnaire. Here we have some results regarding the usability test. In this table, we can see the consolidated report with evaluation results from the experts. So VMAPs was very well accepted by them, indicating a perceived benefit in mixing 2D maps and 3D charts as part of one visualization solution. It's necessary to consider improvement in some functionalities for novice users who have a low learning curve. We identify that. And even though VMAPs is a complex application, involving a large amount of data, as well as conventional interface and interaction. The answer to the usability questionnaire showed a high acceptance rate of the system, obtaining an average of 4.3 points of 5. As mentioned before, our solution integrates two different tools. We have the VMAPs and Cometa. That is a collaborative web application that allows multiple users to discuss web information. So during a collaboration session, users can add multimedia elements like video, images, and text, and also draw some objects, such as arrows, lines, and circles, over the 2D image captured from VMAP's canvas. So this way, Cometa creates a shared workspace where participants can annotate, draw, brainstorm, and convey ideas during asynchronous or asynchronous discussions between participants in the collaborative section. Here we have the Cometa architecture. You also have a visualization model here that allows users to create collaborative sessions and use some multimedia elements and draw objects to increment the presentation. We have here the engine model, the real-time session model that allows users to keep track of the changes as they occur without refreshing the browser. We have draw on canvas, which draws objects of the image. The objects can be recovered from the database. We have voice chat that allows the users to communication with each other, audio and video sharing, and the database, relational database model to manage the session data with the multimedia that we can include the presentation, and the technologies, web technologies that we use to develop the solution, ASP.NET and WebRTC. We also had a usability test for Cometa, working in an integrated way with VMAPs, and it was necessary to consider the use of both tools to evaluate the collaboration. So the same five experts who had already completed the pre-test questionnaire during the VMAPs, tested and performed the following task. They used the VMAPs to visualize weather units about the city of Florianópolis, Brazil, and export the resulting map to Cometa. Using the 3D chart environment of the maps to find the same meteorological events, they found they had to navigate it and export an image to Cometa. Each expert must disclose the meteorological events of Florianópolis and with two other participants, and they were free to use collaborative tools, voice, chat, video, lines, as they wish. And the following steps were performed for the Cometa usability. They were accommodated in computer laboratory. Cometa integration with maps was explained by instructor for 15 minutes. Each expert had 30 minutes to use the tool. The task was explained. Each expert had 10 minutes to solve each task, and each expert had 30 minutes to answer the questionnaire. Here are also some results about the usability test. We consider that reviews were consistent across experts and questions since the variations were not significant. Even though the results are preliminary, they proved useful in the validation of the applications. The experiment successfully demonstrated usability and usefulness of both VMAPs and Cometa as tools for synchronous and asynchronous discussion. And it appears that the user's engagement, motivation, participation, and awareness during the test led them to become unaware of the distance between them and cooperated naturally. Here are some conclusions. This paper represents a web toolset, easy and flexibly facilitate visualization, VMAPs to visualize and analyze 2D maps and 3D charts, and Cometa to allow which allows the collaborative analysis of severe weather, working together with VMAPs. VMAPs and cometas were tested using real data and showed that they fulfill their class of applications performance and stability requirements. Tools such VMAPs and cometa are necessary to study and discuss severe weather events and define research for prevention and anticipation of servicing. At most in Brazil, we had a lot of problems with some storms. And a collaborative tool such as Cometa is necessary to facilitate information exchange among experts to assist the decision makers in taking action efficiently. From the observed results, we can conclude that our work has achieved its purpose. And for future work, we intend to adapt the maps and Cometa to support the visualization, analysis, and discussion of other data such as epidemic information. This research was conducted some years ago, so if you have some questions and I could help you here, I will ask you some email to talk about with Professor Hobson. He was supposed to be here, present the paper for you, but he could not be here today, so I'm presenting the paper for him. He was the leader of this research and I was responsible for the handling communication solutions about the application. Thank you, guys.
Thank you, Diego. We can take some questions, or I have some questions here. These experts that you got to validate the user interface, the usability, did you talk with somebody from the International Charter on Space and Major Disasters?
No, not exactly.
I'm not sure if you know this International Charter. Is an international association. Each country had at least one institute. In case of Brazil, it's Laércio Namikawa at INPE. And
yes,
they have some challenges.
I know him, the name. I know his name. Yeah. I know who's the guy.
What happens is that when we have any kind of disaster that goes from oil spills to tsunamis to any kind of disasters, they have the charter have to collect data from everybody that has satellite in orbit to try to get that as soon as possible and to create a set of data that's used to map what happens. So it's a very interesting collaboration because it's free, of course, free for the users. It's sort of centralized, but it seems to me a very good case use for you. Because they need to get, let's suppose you have something like a disaster, they need to get all the data that they can really quick and put in a repository so people can analyze. And usually when they say very quick, it's just get the raw data and put in a file server. They don't get any kind of interface, it's just put the raw data and everybody have to collect that. And there are some people learning to do quick analysis using QGIS and remote sensing image. So what I see about your tool, about Comet, it seems interesting to reach these people and ask them if they are interested on that. I have your contact here.
Are you from INPE, right?
I'm from INPE.
Yeah. I think it will really be good if you put us in contact with the professor there. I think it's going to be a very nice application for our tool. We have all the code available in a GitHub. I didn't put here, but I think we have it. I think I didn't present here, but we have this link in the paper. But I really want to work together with you guys.
Great. We'll be in contact about that because it seems a very good use case. If the developing time is to get an application running are those that you sent, we have several use cases for that. And I may suggest that we have several use cases, not only on disasters and this kind of emergency, but on other kind of issues. For example, they are disasters, but not that disasters. For example, forest burning, forests in preserved areas. There is a system that monitors that, but we are not in a hurry to put the data publicly. And maybe with this kind of tool, we can try to do that. So I contact you when I get to Brazil about sharing some ideas.
I wait for your contact.
Okay.
Okay. Thank you, Rafa.
Okay. Any further questions? If we don't have any further questions, Diego, thank you very much again.
Thank you, guys.
And I'm going to finish to close this virtual session. Thank you very much for the participants, Maxim and Dimitri. Thank you and see you soon.
Thank you. Goodbye.
Let me see if I can go to my presentation. It's another